Okay, just a couple things I want to mention to you before we start the semester conclusion. Specifically, we're going to have a review today with iClicker 2. It'll be self-paced like the final. We have handouts out here. We'll be handing those out to you in a few minutes. And I'll be converting those, as I mentioned, into some bonus points. A couple other things I want to mention to you. There's a new SSG Schedule page. You may have seen it. I put a new identifying graphic on there, the I can't believe it's not butter image, instead of the red stapler. So if you get to that page, you'll know that you're on the right place to sign up. The link for sign-ups is not activated yet. That'll activate today at 7 p.m., same as last time. You can go there now and see almost all the SSG sessions. There's just a few that need a time and place, but I think about 20 of them are already lined up and ready to roll, ready to sign up for. Couple other things. I was in office hours yesterday with some students. We were working on various problems together, and one of the students asked me to look at exam 3 data, and the student said, Dr. B, I thought I did question number 2 on exam 3, the clicker question. And so I said, all right, I'll go back and look at the clicker data, and because that particular student had not gotten any points from it. So I went back and looked, and there it was. I went searching by his NID instead of his clicker number, and I found everybody else that I looked for, I found there, and most of them were correctly answered. So what I'm going to do for section 1 and also for you guys in section 2 is I'm going to review the exam 3 clicking data and see if I can extract your question 2, and hopefully that'll, it's 3 points. So if you got it right, that's another 3 points on the exam, and that may actually change your exam score, and it may actually change your best 2 out of 3. And so if it changes your best 2 out of 3, it'll change upward. All right. So, and I apologize, the clicking software, I have never had a single problem with it until this semester. And this semester we've had a bunch of problems with it. It's been a pain in the you-know-what. But we're going to try to get to the bottom of it. Matter of fact, we're going to be clicking today with, I got a brand new clicking base unit, this receiver up here. The iClicker representative met with me yesterday in my office before office hours, and she looked at the base unit, the receiver that I had been using, and she said, boy, that thing's been through the wars. And it had been. I've been using it for several years. This is a brand new one. Hopefully it works good. So we'll be doing that. Another thing, it's not in the slide, but you might want to make a note of it. Office hours with me next Wednesday. Okay, I think somebody was going to ask me about that. Office hours with me next Wednesday are from 9:30 a.m. until 2 p.m. So mega office hours. That's 3.5 hours, almost double. All right? And so 9:30 a.m. Wednesday until 2 p.m. Wednesday. And then Thursday and Friday, I'll be photocopying exams like a maniac. You probably will not see a whole lot from me on web courses, but Miss Caroline, our TA, and also Darian will probably be lurking in web courses, discussions, and so forth. So continue to use them. Also, tonight we're going to have a mega review homework as promised, and it will be due, I think I've got it set for 5 p.m. next Friday. So you'll be able to use it as a study tool, and it'll be a big assignment. Right now it has 48 points. I think I'm going to trim it down a little bit, down to 30-something points. Anyways, I'll try to get that running this afternoon, and you'll be able to see it. So, actually, Caroline, could you log into Web Courses and see if that assignment is available? Hold on a second, students. Yeah. Well, it's not going to be worth 48. It's only going to, as I mentioned, it's going to be worth, I'm going to convert it down to 2 or 3 bonus points. Same thing with our in-class review today. So the mega review, I don't know where it is, down at the bottom or something. When does it open?
It opened this morning at 12 a.m. until December 9th at 11.
Oh gosh, that means, hold on a second, student. Okay. All right. Hold on a second. All right. So your guys, the new schedule for SSG is up, and a few people are still left to put their data, for me to get their data in. So that signups is going to be, yeah, see, this guy in front of you's got a big head. He doesn't even know that you're blocking me, blocking my view. But I could hear your big mouth back there, gabbing and stuff. So excited, yes, I know. Anyways, if you don't mind, it's all right. So 7 p.m. tonight is the Stampede Time. So get in there, get ready at 6:59 p.m. and then you'll be ready to get the group you want at 7 o'clock. All right. Now, lecture today is going to be a little bit different. I don't think you actually need to take notes on much, because what I'm going to do is take you through, Justin, pretty much the whole semester and kind of bring it all together for you. So mainly what you can do is maybe take a note here and there, but mostly just listen and see if Zach can refrain from talking, and everybody else on that row. Yeah. And no, nobody up there in the sky. It's you guys. Please, I'm serious. We got stuff to talk about. Okay, so listen and think and take some notes. Now, I mentioned to you in the textbook and in class that this operation that we are in, you can think of it as being a student in the school of Galileo. The entire scientific enterprise began with him in the distinctive features that we now think of the scientific enterprise. The first thing that we did on day 2, lecture 2, August 25th, and make a note of it, we've got, for a lot of the slides, not all of them, but many of them, I've actually keyed in the date and the lecture that we covered these topics. First thing that we did on lecture number 2 was we observed the spectral lines of hydrogen. We also looked at helium, and we looked at neon. And we've been talking about those elements since then. Observation, essential. The other thing that we've emphasized is the language of the universe itself. And I love the way that Galileo wrote about it. He said, philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it is written. It is written in the language of mathematics, and we've done a lot of mathematics together. Some of it's pretty serious mathematics. You guys didn't really realize it, but we've done some serious math together. And I'm glad to do that with you. Its characters are triangles, circles, and other geometric figures. And we've done a lot of geometric figures together, including ellipses, without which it is humanly impossible to understand a single word of it, meaning that book. Without these, one is wandering about in a dark labyrinth. Now, the dark labyrinth is the bottom of the mountain. And we've been walking up a mountain. This is like the first day of our journey up this mountain. How do you get from point A to point B? Very basic question that a scientist has to know and be able to figure out. One of the things you got to know is Pythagorean theorem. Remember that? The calculated distance from point A to point B. Another thing that you want to figure out if you're a scientist, Sabrina, is when are you going to get to point B? You remember, the whole scientific enterprise, or a big portion of the scientific enterprise, is oriented to our desire to predict some future state. In this case, predict when you're going to get to point B. And that was just for constant motion. What if you're accelerating? When do you get to point B if you're accelerating? Now, here's a dragster. And this dragster has a negative acceleration. In other words, it's losing speed. How do you know it's losing speed? Because it's popped its chute. Okay? And that's what they do to slow themselves down. They don't have hot brakes on those babies, but they do have that chute. And that helps the regular brakes that they do have. Okay, so he's losing speed. He's losing forward speed, so that means his acceleration is actually backward. The brakes, Adriana, exert a backwards force. Or if we were thinking forward positive, backwards negative, it's exerting a negative number of newtons from the brakes and from the chute. So accelerated states, accelerated motion. The famous example, or the famous experiment that Galileo tackled was this one. The Leaning Tower of Pisa. He dropped two objects down, one big, one small, to see if they timed out just right. I observe a stone initially at rest, falling from an elevated position and continually acquiring new increments of speed. Now, that's something we talked about in Lecture 4 on September 1st, exactly 3 months ago. And this was the famous statement where it actually is an implicit definition of acceleration, continually acquiring new increments of speed. You know, that dragster, as long as it was in motion with the chute open, it was continually losing increments of speed. So in free fall, something's acquiring additional increments of speed. And this was the famous area where Galileo said, you know, I want to know about accelerated systems. Let me focus on free fall, because free fall is the simplest of all the different accelerated motions you can think about. You know, if you're in a boat at sea and you're going over the waves, and you know you're seasick, hopefully not, but you know you're in an accelerated system, very complex accelerations. You're going up, you're going down, you're going forward. Hopefully, you know you get a little bit of headway through the oceans, and but you know your state of motion, your velocity vector is continually changing. Very difficult accelerating system. Okay, free fall, very basic, and that was his strategic choice. Another thing that we used for that is, remember this example from the Mines of Moria, and Peregrine took. He dropped that little thing down, a bucket or whatever it was in the movie, and he alerted all their enemies. And we used that as an example to figure out the drop distance. How do we figure that out? We use the distance triangle. Remember that? Here it is, the distance triangle. We mapped out an abstract picture of velocity, v, on the vertical axis and time t on the horizontal axis. And we said, all right, let's interpret the area between the velocity graph, that's this line at 45 degrees, and the t-axis, the horizontal time axis. Interpret that area as the distance traveled, and it's possible to do that. Matter of fact, this is the essential triangle that all these, half the PhDs on the planet use this and other triangles like it when they're trying to figure out the position of a spacecraft. And they use much smaller delta T's and a lot of them, and they do a lot of distance rectangles, a lot of distance triangles, and that's what their computers are doing. And they're doing it in 3 dimensions. And so, but basically, this is what they're doing. And the distance triangle. So this is now remember, this is a distance. It's not a coordinate. It's not a position. It tells you how far something falls from rest. To get the y coordinate, it's a little bit different. But we did that too about this time. Another thing we did in lecture 5, we started talking about Newton's 3 laws of motion, and we've never stopped. We're continually applying this whole idea that Sir Isaac Newton said, yeah, if you want to be able to predict the future state, the position or the dynamics of a system, you've got to know the accelerations of the system and be able to measure them. And so this is his famous second law, F net equals ma, or in this case, A equals the quotient F net divided by m. His first law was the law of inertia, and his third law was the law of action and reaction. And we talked a lot about that, especially in the context of skateboarders. And in the context of skateboarders, we introduced a new concept that we actually brought to bear with discussion of Planck's constant. Because Planck's constant, the one constant that rules them all, must be wrought in terms of momentum, and in fact, angular momentum. And remember, in an interaction between skateboarders or any other two systems, the coin of the realm, the thing that is exchanged, is momentum. A little bit of leftward momentum exchanged and a little bit of rightward momentum, delta P. You know, the amount of momentum one guy acquires is the exact same size but opposite of whatever the other guy acquires, all right, in an interaction. Now that applies to collisions. And we studied boxcar collisions, and, the one coming in from the left with some speed and the other 3 or the other 4 at rest, and we figured out how to calculate the new velocity of all 4 of them moving off to the right afterwards. So the future state, we were able to predict the future dynamical state of the set of boxcars after they had latched together using the conservation of momentum. Here's another complex system, very complex. You can use momentum to understand this interaction. 2 galaxies interacting, they're close enough together that the force of gravity is mediating momentum exchange between these 2 complex galaxies. So they're being pulled all out of shape. A galaxy by itself is going to be, in a disc shape, maybe with some spirals, maybe without. Sometimes you'll see an elliptical galaxy. But if they start interacting with one, and if it's close enough, it'll get all discombobulated. And these 2 are in the process of getting discombobulated. Another thing that we started talking about necessity was uniform circular motion. Remember we talked about the Nardo ring. That was lecture 7 on just before exam 1. And so lecture 7 on September 13th, yeah, we talked about centripetal acceleration, and we started laying the foundation for angular momentum, and we built up angular momentum after that exam. And why is angular momentum important? Because the Planck's constant. Planck's constant comes in units of angular momentum, or action. That's the really fancy term for it. And as you may have noticed, yeah, Dr. B's kind of a maniac talking about Planck's constant. And the reason for that is it is important, Planck's constant, the one constant that rules them all, as we have come to learn. Soon after that, after exam 1, we started talking about energy, kinetic energy, potential energy, energy levels. And this is energy levels of a 2-liter bottle of Mountain Dew. So we figured, all right, this is about 2 kilograms. Let's work out GPE, gravitational potential energy, kinetic energy, and stuff at different energy levels. And you know, I used the term energy level there because I knew that at the top of the mountain, Morgan, I was going to want to talk about atomic energy levels. The energy levels for electrons, because those are the energy levels that are really interesting. Those are the energy levels that control the dynamical state of the electrons around an atom, and then how those atoms bind together. Another thing that we did with energy, we extended it using the e pluribus unum concept to talk about heat energy. And that was about lecture 15 on October 11th. You know, the e pluribus unum concept, from many one, out of many one. So the whole idea of that is we have this big moles, this big molybus, a big blob, a shapeless bulk of atmosphere or gas. We can't see the individual molecules, but we can model them theoretically using F equals ma, using energy, using momentum exchange, using angular momentum exchange, and extract with a little bit of calculus and a little bit of stats and a little bit of trig, some macroscopic measurements. That's the unum. The pluribus is all the zillions of little molecules you can't see. And Chelsea, the unum is temperature, pressure, and other macroscopic variables that describe a gas. So for instance, the temperature is directly proportional to the average of all the kinetic energies of those zillions of molecules. The pressure is related to the exchange of momentum of all those zillions of molecules with the rigid containers, the rigid walls of the container, whatever the container is. Right? That's how you get pressure, through momentum exchange, and zillions of them. After that, yeah, about lecture 17, this is after exam 2, we started talking about the good old heat, melt, heat. Remember this one, the polar bear? We worked that one out together in class. Yeah, heat, melt, heat. And that is a result of the e pluribus unum concept, using good old Sir Isaac Newton to figure out how do things melt? How does the temperature change? How does the unum change as you add energy? Unum, temperature. The temperature is the unum of zillions and zillions of pluribus molecules in a gas or a solid or a liquid. And yeah, heat, melt, heat. That's one of the things that we worked on as a real brain burner. Here's another one. How is it that things get so hot that they turn red? That's radiant energy. energy transport. We talked about conduction, convection, and radiative heat transport. All right? And this SR-71 is kind of a famous example of a plane that can travel so fast. If it's low enough in the atmosphere and going fast enough, it'll actually get so hot on the leading edges of the wings, the nose, the tail fins, and so forth, that it'll glow red. And at night you'll be able to see it, even though it's painted black. And I've actually seen it at night when it's doing that. I didn't know that's what I saw, but we later figured out that's what I saw. Famous UFO that we later figured out was this SR-71. This is about 20 years ago we saw that. And why is that interesting for us? Well, that's the context in which Max Planck developed his constant, H. He was working on the spectrum of hot objects, incandescent objects. And I mentioned how, nobody could figure him out until he made his assumption about the quantum of energy using the constant H. After that, we started talking about waves and oscillatory systems. We had springs and the spring constant, 1/2 kx squared. We talked about diffraction. And here's prototype wave phenomena. Wavelets form, and from the wavelets you observe diffraction. We observed diffraction lines on the second lecture of the semester when we looked at hydrogen and helium and neon. And this is a picture that we talked about on October 25th, lecture 19. And about the same time, actually, let me just reinforce in this diagram, my cursor's kind of small, but right down here, right above the gap, here's the gap. The wavelets form in the gap. And right above that, you have a lot of wave energy. You can see the bright white bars proceeding, but there's a little bit of curvaceousness to them. All right? Now, they're not curvaceous down below the gap, down here. That's incoming. Those are flat plane waves. Okay? But after the gap, the wavelets form that curvaceous set. And actually, you can see here just barely a little beam of energy off here to the left and to the right. You can see it over here on the left a little bit better. And that's where you get the red and then the aqua and then the two purpley lines from the spectrum of hydrogen. Right? Another thing that we talked about to describe a dynamical system, especially oscillatory systems, periodic systems, is the phase diagram or the phase portrait. And the units of this also are important. Did you know that cardiologists use phase diagrams like this? They do a slightly different version of it, but they trace your heartbeat. If you have a good, what they call a sinus rhythm, sinus meaning curvy, up and then down like waves in the ocean, and up and then down again. Sinus rhythm. The phase diagram for a heart, the heartbeat in sinus rhythm is a perfect circle or ellipse. Okay? So any kind of periodic system, even your heart. And did you know that a heart that's that's fibrillating is all over the place? A heart in fibrillation is, it's all over a phase diagram. But a good steady heartbeat, ba-bum, 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 ba-bum. Nice and smooth, nothing but net. A perfect ellipse, or pretty close to a perfect ellipse. And there's the energy function. The energy 1/2 kx squared plus 1/2, 1/m times px quantity squared. Yeah, that's actually the equation of the ellipse in phase space. You can dress it up and figure out all the height and the dimension of it. Yeah, maximum rightward position, maximum positive momentum. It's all related to that. And the area of that ellipse comes in units of angular momentum. And as hopefully you're starting to understand, that is important to understand Planck's constant. The one constant that rules them all. The one constant that affects the dynamics of an object, no matter if it's being gravitationally forced, electromagnetically forced with a Coulomb interaction, or one of the two nuclear forces, the strong nuclear force or the other one, the weak nuclear force. The four forces of nature, objects all have to deal in some manner, shape, or form with Planck's constant. Coulomb interaction, we talked about this after we talked about waves. We talked about Coulomb's torsion balance. That's about lecture 21. This is a month ago, November 1st. And the electroscope, which once Coulomb figured out, the forces, we could figure out and do a little trig and figure out, how many electrons are on those leaves of foil that force them, 20 degrees apart versus 30 degrees. If you have 30 degrees, you have so many electrons. If you only have 20 degrees of separation, you have a different number of electrons or protons. And that led us into this one. Now this one, the brain burner, the linear charge array brain burner, is the one that for us gets us thinking, Sean, in terms of molecules. In other words, this linear charge array is a decent prototype of a true molecule. Now, a true molecule is not necessarily going to be equally spaced between all the charged objects. Okay? In fact, a true molecule might not even be linear. It might have a hexagonal shape. When you buy gasoline at the store, you're buying molecules at the store, at the gas station, wherever you get it from Wawa or something. You're buying molecules that have specific shapes, octagonal shapes, hexagonal shapes. Yeah, and those are the ones that give you fuel. Octane rating, 8 octane. The more octane, the more power per ounce, per gallon of the fuel. Another thing that we talked about after that was atoms themselves. And we talked about, for hydrogen, the Balmer series. Oh, Lord. Okay. The Balmer series. And we thought, this whole idea that there's an observable regularity in the spectral lines of hydrogen, the Balmer series. We found that, or we didn't find it, Balmer found it, 1 over 2 squared minus 1 over n squared, and that was related to 1 over the wavelength. How he figured that out, I don't know. Maybe somebody knows, I don't. But he figured it out, and that is a quantum pattern. It involves counting numbers, n equals 3, n equals 4, and on up for Balmer series. And that means that there's some kind of regularity that we can't see in the atom, because remember, we're still on the e pluribus unum situation. We can't really look at an atom. We can barely even now, Balmer's day, forget about it. The last 10, 15 years we've been able to look at some molecules and see their shapes. But yeah, this thing here tipped us off eventually that Planck's constant was going to figure in some way to figuring out that regularity that we could see in the spectral lines. And we thought, all right, Planck's constant is going to be some numerical measure, or is going to enter into some quantity that explains that regularity. And the explanation was the one that Louis de Broglie figured out about 90 years ago in the 1920s. And he said, let's treat an electron like a photon. We think of a photon as being a particle that also behaves like a wave that also behaves like a particle. Let's think about electrons that way. And if we think of an electron with wave properties and insist on constructive interference, then yeah, we can think about everything works out for the hydrogen atom. This whole spectrum that we've looked at, H alpha, H beta, H gamma, H delta, and all the other series, they all make sense if you insist on constructive interference. But prior to him, nobody thought about electrons. They thought they were little teeny electrical nuggets, like little BBs or little baseballs that have electric charge. But no, he said, if you think about them as waves, it all works out. The other way to think about it was in terms of quantum leaps on a phase diagram. And in a phase diagram, and this is one for an oscillator, you can do a similar one for an atom in the Coulomb interaction, but for an oscillator, the whole principle is to jump, to make a quantum leap from one ellipse, and that ellipse shows all the dynamical states of an oscillator, down to a smaller ellipse, another entire set of dynamical states, only if the area changes by multiples of Planck's constant. So this is where Planck's constant comes into full view in this quantization scheme, where your ellipses change in units of h. So the change in the area is h, another change 2h, another change 3h, and on down as far as we can go. And then finally you'll run out of states, you'll be at the ground state. All of that allowed us to tackle the periodic table. The periodic table was first figured out by Professor Mendeleev over in Russia. And he said, look, if you map out the atomic weight of elements and you put them in stacks or put them in rows, whichever you like, then each stack or each row will have similar properties. And he said, this cannot be a coincidence. There's got to be a reason for it. Now, Professor Mendeleev did not know anything about electrons or anything, but he did know about the properties of different elements. He even predicted where some of the elements would go. Germanium up here, Ge. Let's see, the other one that he predicted, scandium, which is over here, Sc, and I think one other one that he predicted, and somebody found them. From that table, we can figure out why atoms combine the way they do. The atoms are all trying to get their outer energy level to look like the energy levels of helium, or maybe the energy levels of neon, or the energy levels of argon, or krypton, or anything else in this right-hand column, the noble gases column. And that's what happens with CO2. We talked about this just Tuesday. The carbon loses 2 electrons, or shares 2 electrons, to one oxygen, another 2 electrons to the other oxygen. They bind together by covalent bonding. And now the oxygens feel like, yeah, I've got an outer energy level that's full, and it's just like the outer energy levels of neon. And then the carbon in the middle is feeling, yeah, I've lost a few electrons, I've shared them out, but now my next level down is like helium, it's full. And that's what elements like to do. There's other molecules that we can talk about. This is the one I love to think about, retinol. This is the one in the retina of your eye. When a photon interacts with the retinol on the left, that's the folded one, the photon energy is deposited into the retinol, and the retinol snaps to its elongated form on the right. Right? And then a short amount of time later, it collapses, it relaxes, it loses energy, and it relaxes back down to the folded form on the right. And that is how the retina of your eye sends impulses down the optic nerve. Everything that you can see at this minute is because you have pluribus retinols doing their thing in response to pluribus photons coming in through your eye. It's lovely to think about. There's other molecules to think about. Here's one of the most famous, DNA. Photo 51. That was taken back in the late 40s or early 50s. I can't remember exactly. I looked it up once. That was the one that allowed Watson and Crick to figure out, helix, double helix for DNA. At that time, in the early 50s, everybody was trying to figure out, they knew what DNA was. They knew that it was the molecule of life, the genetic code, and they were trying to figure out how do you store it? What's the structure of it that allows it to store an entire genome, which is what it does. And so they eventually figured it out that it was the double helix. All these molecules, they're all ruled by Planck's constant, the one constant to rule them all. But there's something more that I want to tell you about. And this is something beyond Planck. Right? So I've been hitting Planck's constant all day today. But now I want to go a little bit more. We're up on the mountaintop. We've looked at the periodic table and compounds. And we could take another whole year and talk about nothing but different compounds and how they work. And that would be lovely. But I want you to think about this. This is where I want you to conclude the semester. A guitar and a little slice of DNA over here. This is kind of a close-up view. DNA, a molecule. And the molecule binds together because constructive interference occurs at certain distances and energies, and only those distances and energies do you get constructive interference. And that determines the structure. In the case of DNA, the double helix. Compare that to a guitar. Remember that? We had Justin up here giving us a demonstration of the guitar. And you guys might have been pretty bored. Okay, Dr. B, nice, a guitar, tunes. But we had a guitar. We played a string. We detuned it. It went a little flat. Then we tuned it back up. And we played some chords. Those strings, each one, if it's in tune, has a very specific wavelength because of constructive interference. You might want to jot this down. The DNA, this is the only part that you might want to jot down in your notes. The DNA structure is basically a lot of constructive interference with a lot of different atoms. The guitar, when Justin strummed a chord, each string produced a certain note and only that note because of constructive interference. So when he strums a chord, it's several different strings that make a sound that we consider to be beautiful and graceful because of constructive interference. Now compare that to the DNA, a bunch of atoms that are binding together to encode life itself because of constructive interference, just like what a guitar does. And everybody knows that guitars, music is powerful. They say that the most powerful, that the man who's going to change the world is a man with a camera. And I've heard people say, no, man. It's the guy with a guitar. Music. So think about DNA, not just as music, but as a set of instruments, all working together to make a beautiful symphony. What is that symphony? The most beautiful symphony of all. Us. All right, that's my final comment. We've finished the semester together. And I just want to tell you that the way I look at things, this is just the cover and the title page. We got a lot more to learn. There's more mountaintops ahead, further up and further in. And the more you stay with it, the more you will learn. So thank you for being great students. I've enjoyed every minute of the semester. Now, and I'll give you guys a hand too. You guys are great. Now, let me get my cursor here.